Oh, oh, there, got it.
Okay,
Just appeared.
great. So, welcome everyone to this week's Origins Colloquium. It's a real pleasure to introduce Bruce Strain to give the talk this week. Bruce received his PhD from Cornell in 1978, theoretical physics. He was then a postdoc at Harvard and the Institute for Advanced Study before joining the faculty at Princeton in 1982. And Bruce has literally written the textbook on the interstellar medium and intergalactic medium. His interests are wide-ranging: interstellar shocks, PDRs, and of course, interstellar dust. And today we're going to hear about exciting results in this very low metallicity system. So welcome, Bruce.
Thank you very much, Jonathan. Thank you for the invitation. I'm very happy to have this opportunity to share this work. I'm going to talk about dust in a one particular galaxy, one Zwicky 18. I'll explain why we're interested in that in a moment, tell you what we've learned about the dust. And then later, if there's opportunity, I can also talk about some things we learned, some surprising things we learned about the molecular hydrogen in this galaxy. But I'm going to try to focus on the dust for this presentation. Okay, so why is one Zwicky 18? Well, obviously, we'd like to understand the first generation of star formation, the early stages of the evolution of interstellar media in galaxies long ago, far away. And we're beginning to be able to do amazing things with JWST and ALMA and so on. But still, if we want high spatial resolution, it'd be nice if there were something that was an analog of a very young system at high in the early universe, more nearby that we could study. And so if we can find a very low metallicity galaxy that is relatively vigorously making stars today that isn't too far away, well, we may learn things from it that will inform us about how things might have gone at redshift 10 or 15 when the bulk of the vigorous galaxy formation was just getting underway. So 1 Zwicky 18 is such a galaxy. It's 18 megaparsecs away, so not immediately in our solar neighborhood, but not particularly far away either. And it has a metallicity of only 3% of solar. So among low metallicity galaxies with star formation, it's down there among the lowest that we know. So here's an image, HST image of 1 Zwicky 18, just showing you what it's like. The bulk of the galaxy is down here. It has a companion up here that is associated with it, but we're not going to talk about that today. We're going to talk about the things that are going on in this star forming system down here. It's known as a blue compact dwarf galaxy. Let me say I'm very happy to be interrupted at any time for questions. So just find some way to, raise your hand and I'll look for it here, or Jonathan will stop me. Okay, so just remind you of the usual notation in astrophysics of capital Z. When we're discussing stars, capital Z is the fraction of the mass of the star that is not in hydrogen or helium. In other words, all of the heavier elements are summed in the letter capital Z, and the sun has a value of capital Z of about 1.4%. Everything heavier than helium is only 1.5% of the mass of the sun. We could also measure the mass of dust relative to the overall mass of the system. Dust is always a minority constituent. So we can take the ratio of dust mass to gas mass and call that Z dust. So how can we measure Z dust? Well, yes, we can. We can measure it in the Milky Way. We have a pretty good inventory of the dust mass in the Milky Way. It's, not a precision. We can't do precision measurements, but to the extent that we can do our best job of estimating the dust mass in the Milky Way, it's about half of the total heavy element mass. So the Milky Way is able to put about 50% of all of the heavy elements heavier than helium into solid form in the typical interstellar medium. It's lower in some regions where dust has been destroyed by vigorous shocks and so on, but this is a typical value. We try to do this dust inventory for other galaxies. The way we do it is the best method is to not try to estimate dust from extinction or something, but rather to estimate the dust mass from the thermal emission that we observe from the dust that is warm enough to be radiating. And warm enough means in this era where we have sub-millimeter and far infrared sensitivity, it means basically all the dust is warm enough to be detected by an instrument such as Herschel Space Telescope and other space observatories. So we've done that for a number of galaxies where the signal to noise is high enough to do a good measurement of the dust mass, and where we have information on the gas mass from 21 centimeter or carbon monoxide observations. And then here's a plot from a 2020 paper summarizing the data from the kingfish, primarily from the kingfish sample, of the dust mass as a fraction. Plotted here is hydrogen mass, not total gas mass, so it's not quite Z. But galaxies up here, these are normal metallicity galaxies, and they all tend to have dust detections. And the dust detections tell us that, again, the story is that about half of the heavy element mass seems to be in the form of solid particles. But if we try to do the same exercise on galaxies with lower metallicities, where we can measure the gas because we have enough gas to measure CO and 21 centimeter. Sometimes we don't even detect the dust emission, and we get dust upper limits on the dust mass, which can be well below the trend line that you'd have here if you had all of the Z dust of Z over 2 would be a trend line that looked like this. And many galaxies are, well below that. So we know that low metallicity galaxies have trouble turning their heavy elements into dust. They're not as successful at doing it as the Milky Way or normal metallicity galaxies. Okay, so that's the motivation for studying 1 Zwicky 18. Here we have this very low metallicity galaxy. Are we able to detect dust in it, and what can we learn about the dust in it? So the parameters of the galaxy, the total mass of stars estimated from models of the stellar population in this galaxy to reproduce the observed light is only about 20 million solar masses of stars. 21 centimeter detections are solid. We have a 21 centimeter determined mass of H1 of about 10 to the 8th solar masses of H1. So this is a small galaxy. This is not a main sequence galaxy in the sense of the Milky Way or others, but nevertheless, it's a galaxy with interesting activity in it. So if we take an image of the same galaxy with JWST, here's an image taken through 1, 2, 3.5, and 4.4 micron filters, colorized in a way that we won't get into, but it's basically looking at the emission from the stellar population, which includes some older stars, which are, evolved stars emitting more strongly in the mid-infrared than they were in the HST image taken at optical wavelengths. Okay, so the star formation rate estimated from HST is in the range of 0.2 to 1 solar masses per year. It's surprising to me that there's that much uncertainty because it can also be estimated from free emission from the ionized gas in the galaxy. But in any case, a value something in the range of close to 1 solar mass per year of star formation has been going on for at least the last few million years to give us the population of hot stars that we see there. And so we can talk about the age of this system, take the current the stellar mass of 20 million solar masses, divide it by the star formation rate, and we would have a characteristic age for the system of only about 10 to the 8th year. So a very young system. Again, maybe this will tell us something about what's going on in the early universe. The metallicity of this system is 3%, which translated into Z is about 6 times 10 to the minus 4. So well below this 0.014 value that we have for the Milky Way. Okay, so the dust in this galaxy has been searched for in the past. Spitzer Space Telescope did detect it with Spitzer observations, and then it was revisited with Herschel to try to get better angular resolution and better sensitivity for the emission coming from a very compact region here. So these two images here are Herschel. The color is a Herschel image at 100 microns and 160 microns. The white contours here are 21 centimeter contours. So this is showing you where the gas is in this galaxy. And in this image, north is up. And so we see that where the 21 centimeter emission peaks, there's a very clear detection in the PAX 100 micron far infrared filter. 160 microns, well, looks like a detection there as well, but it's not particularly strong. We see a number of other sources here. If you look at the sky at 160 microns, well, there are lots of things that show up that are, some of them are great distances, but it does appear that we have a detection here at 160 microns. But this is, I'd say this is a very confident detection at 100. So if you try to put together a story of how much dust there needs to be to explain this observation and observations at shorter wavelengths with Spitzer. So this is Spitzer 24 microns and Spitzer 70 microns with, 70 microns is a pretty big beam compared to this, but they can sum up the power in that beam. And if they attribute it to the galaxy, here's what you get. You can make a model for the emission. And so this is a paper by Fisher et al. In 2014, where the spectral energy distribution could be explained with a distribution of dust temperatures, but with a typical dust temperature being something like 50 degrees Kelvin to get the peak happening up here around 70 or 60 microns, and with a dust mass of maybe 1,000 solar masses for reasonable assumptions about what the dust properties might be. Again, we don't know what kind of material this is, and so we don't have any certainty about what the opacities are, but for a range of plausible opacities of dusty candidates, the dust mass is something like 1,000 solar masses to explain this observed emission. So what dust mass fraction of the heavy elements is that? Whoops, this should have been, yeah, okay, Z dust over Z solar is, instead of being the value of a half that we would have in the Milky Way, it's only about 1%. So this galaxy doesn't have very many of its heavy elements in dust, at least according to this estimate of the dust mass. Okay, so let me remind you about what we know about dust in the composition of dust in a galaxy like ours. Well, at this point in time, I think we know quite a lot about what the composition of dust is in our galaxy and in the few other galaxies where we have pretty good ability to study it, but mainly based on the Milky Way. So we know from a variety of pieces of evidence that I'd be happy to talk about later, but we don't want to review now, that the bulk of the dust mass in the Milky Way, and I'm speaking now of the diffuse interstellar medium where we don't have a lot of ices, is made of amorphous silicates material. Exactly which amorphous silicate composition, we could argue about that. But the evidence for silicates is strong, and we need a substantial amount of silicates to explain what we see. But we also find that when we try to make models with just silicates, they don't work. There's a number of ways they fail to reproduce the observations. We need some non-trivial amount of hydrocarbon material in addition. Exactly which hydrocarbons, we can discuss that. Probably a range of different kinds are present, but they're not trivial in terms of the fraction of the total dust mass. And then in addition, we find when we've done this modeling, we're still left with some iron that we haven't fully accounted for, that we know is not in the gas. It's in solid form. We're not sure exactly what solid form it's in. There could be metallic iron there. There could be iron oxides. So there are minority constituents in the grains that we still are not sure what chemical form they're in. But the bulk of the material is silicates with a significant amount of carbonaceous material present. And I won't review the evidence for this, but the slide here describes the primary lines of argument. Now, where does this dust come from? Well, that's been a long-standing story. Back in the 70s, we discovered that if we looked at evolved stars, we sometimes found evidence of dust being present in the outflow of the winds from red supergiants and other NAGB stars. And we furthermore found that different kinds of stars gave us different kinds of dust. If we looked at oxygen-rich stars, we'd find evidence for silicates. We looked at carbon-rich outflows. We didn't see any evidence of silicates, but sometimes we would see silicon carbide, and sometimes we'd see just featureless emission that would be consistent with some form of, say, amorphous carbon. And so we had stellar sources that we knew were making dust that actually made the kinds of dust materials that we think we need in the interstellar medium. So that looked like an interesting part of the story. But when we thought more about it, we concluded that actually the interstellar medium is a very violent neighborhood with shocks running through it frequently, and frequently enough that when you calculated what should happen to dust grains when a shock overtook the gas that the dust grain was sitting in, that dust grain destruction should be a fairly rapid process, rapid in the sense of being rapid compared to the turnover time of the interstellar medium that would be on the order of billions of years. And so the dust would be relatively quickly destroyed. And so if all we had to rely on was the dust that came from stars, we would not have expected to find a very large fraction of the heavy elements to be in solid form in the interstellar medium. So when we do observe that the heavy elements are primarily in solid form, now I say primarily, maybe half of the heavy elements are in solid form, but if we look at something like iron or silicon or titanium or aluminum, we find that almost all of it is missing from the gas and is in solid materials. So there must be some ability of the interstellar medium to reform solid material. And in my opinion, most of the solid material that we find in our interstellar medium is actually solid material that was grown in the interstellar medium with a significant but minority contribution of solid material as it came from stars. So that's my take on our interstellar medium today. What is 1Zwicky 18 going to look like? Just to remind you that because of the very low, first of all, low dust abundance, if you're going to grow solid material in the interstellar medium, it's very hard to do that directly from the gas phase. So the natural way to do it is to grow onto a pre-existing grain surface. And 1Zwicky 18 doesn't have very much pre-existing grain surface today. So growth onto that grain surface would be slowed by there not being very much grain surface, and then further slowed because there's not very much heavy element, very low abundance of the things that could grow running around in the gas. So we expect the growth process to be very suppressed in 1Zwicky 18. So I'm going to tell you about results from this paper led by Leslie Hunt, published last year, reporting JWST observations with the MIRI spectrograph of 1Zwicky 18. So here is an image of 1Zwicky 18 made from three bands. One of them is HST. So the blue light here is showing you, where the star formation is. So star formation is strong up in this region here, as strong as evidenced by visible stars. And then the green and red colors here are MIRI filter photometry at 5.6 microns and 11.3 microns. So I'll focus on the 11.3 micron emission. We see there are three bright knots down here and hints of red, red at a few other spots here on the body of the galaxy, but three regions stand out very brightly here. And so there's something going on there, not just stellar emission. So the brightness here at 11.3 microns is not starlight, and it's not light coming just from planetary nebulae or something like that, or ejecta from supergiant stars, the winds from supergiant stars. It's interstellar medium. Anyway, this is the region where the spectroscopy has been carried out in the 5 to 28 micron range. And I'll be discussing the extractions of the spectra from these spots on these three bright regions here: JWST Southeast 1, JWST Southeast 3, JWST Southeast 2. And then spectra were also extracted in a number of other circular apertures here. The apertures are 1.3 arc seconds in diameter, which corresponds to about 100 parsec physical dimension at the distance of the galaxy. So we're not looking at just one small cloud or something. We're looking at regions that are showing up here as being bright. Okay, here's what the spectra look like. So they're noisy. This is a very weak signal here. I'll call attention to you that the spectra show very conspicuous emission lines. So these lines here are all strong detections of a number of things, mostly ionic lines. Hydrogen recombination lines are present here. Molecular hydrogen rotational lines are present in the spectrum, not detected at every position, but at many positions. But we're focusing on the dust for the moment. So if you look, say, at this particular position down here, that's the position called northwest in the previous thing. There's really not any evidence of continuum emission out here. It's more or less consistent with zero. You could argue about whether there's a significant excess over zero, but it's really down there in the noise. But if you took this position here, Well, this is where the zero level for that position is. That's a very significant detection of a dust continuum in addition to the emission lines. And several other positions here also show very significant excess over where the zero level is estimated to be. So we're going to look primarily at those spectra that have a strong emission, and all the ones with strong emission not only have a continuum, but they have a continuum that seems to have a feature in it. So there's a feature in excess here that looks like it's peaking at about 14 microns. I would also note that when you look at these spectra, if you start looking where you might have expected to see PAH emission if it were present, well, the data are pretty good here in the 11.3 micron region. There's just nothing there that you could imagine was a PAH feature. Obviously, there might be some PAHs there, but we're not detecting them. Another place you might look would be 7.7 microns. The data are noisier there, but normally that's a place where pH emission is strong. There's no hint of anything here. So this is a galaxy where we looked for the pHs and only get an upper limit. And I'll also note that you can't see it from this spectrum because I didn't plot 20 microns out here, but the continuum emission here we will see has no evidence of either 10 micron or 20 micron emission. The 10 micron emission is within this range, but there's no evidence of anything associated with silicates showing up there. It doesn't mean they're not there, but we're not detecting them. Okay, so we take these spectra, which I just showed you. They have strong emission lines. They're very interesting, but let's measure them and subtract them. So take the spectra, subtract the emission lines. Now the spectra is still pretty noisy, so we're trying to look for broad emission from dust. So let's take those D-line spectra and smooth them. So the black line at these four positions here, so three of these are these three southeast 1, southeast 2, southeast 3, and the fourth position is in the northern part where the position called VLA Northwest A, which also showed a little bit of a red color in that image that I showed you previously. So the black line is the data after delining and smoothing, nothing else. Now, there are some colored curves here that are models. We're trying to reproduce what we see here and ask ourselves what kind of properties would the dust have to be? And the first property we worry about is, well, how warm does the dust have to be? So we need to make we don't know what the material is here, so we need to make some assumptions about what kind of a dust opacities might be there. So let's assume a very simple model of an opacity going with wavelength as 1 over wavelength squared, a new squared opacity. Many materials in the far infrared and mid infrared behave in a way similar to this. So this is a good starting point for what the continuum opacity might look like. Say, amorphous carbon would be more or less described by this. So take that opacity, and then we need to have more than one temperature here to reproduce the data. So let's try, just for simplicity, just two temperature models here. So here, the two of these curves, the dash curves in here, are each the contribution from a lambda to -2 opacity by dust at 50 degrees Kelvin and dust at 100 degrees Kelvin or 120 degrees Kelvin in some of the models, or 110 in this one. So we can reproduce the general rise here from 10 microns or 12 microns, where you first think you're reliably detecting things, out to 27 microns, where the data begin to get very noisy, with this simple combination of these two power law opacities with two different dust temperatures. But we're left with a bump here. So that model here for this position here would give you this solid red line as the sum of those two dash contributions. And there's very clearly an excess here. So we're going to try to model that excess empirically by just saying, let me just guess an opacity feature, the wavelength dependence of a feature that would be able to reproduce this. And then later I'll ask myself, can I find any material in nature that looks kind of like that? But right now it's just an empirical feature here. And if you look at the four positions here, they're not all the same, but three of them are reproduced pretty well with this profile here, where all I've done between these different regions here is I've allowed myself to scale the strength of this up and down a little bit relative to the continuum. So the shape of the profile is the same in all four of these positions. and the profile just scaled up and down as needed to try to give the best overall fit to the observations. So I'd say this is not a perfect fit. There looks like maybe a little bit of additional emission up here, but as a first cut, this particular profile, seems to be about as well as we could do right now. When we do this with a reasonable estimate for what the magnitude of the opacity is, so we need to not just a wavelength dependence here, but a magnitude for the opacity, with an opacity that will be representative of various materials like amorphous carbon, we would have a dust mass of something like 150 solar masses needed to explain the emission just in these four apertures. And I'll point out to you that that's not far from the dust mass that was determined here, where for the overall galaxy, the total emission from this region over the entire body of the system would be a dust mass of something like 1,000 solar masses. We're already up a significant fraction of the total dust mass in these four apertures that we looked at. Okay, what kind of material might this be? So getting to the end of the dust part of it here. Um, Short answer is we don't know. We're still trying to figure it out. But having looked around for candidates, and let's see, what does a candidate have to be? Well, a candidate has to be something that is made of relatively abundant elements. We don't want to start looking for some compound of zirconium or something. There just isn't enough zirconium in this galaxy to explain what we see. We need to be talking about the more abundant elements. And we need to be talking about materials that we know are tough, that are high materials that could survive perhaps in formation and stellar outflows, and then in the interstellar medium of this galaxy. So what I've plotted up here is the empirical profile. So this is what I showed you before, the lambda to -2 opacity with this empirical profile added. Here is just the shape of that empirical profile in a normalized way, where peak value is 1 and drops to 0 at these 2 points here. The colored curves here are calculations based on estimates for the dielectric function of different forms of Al2O3. So a material known as alumina, the chemical material is alumina, when it's in a particular crystalline, the dominant crystalline form that we find in nature is alpha Al2O3. When it's in the crystalline form, we call it corundum. When it has just the right kinds of impurities in that crystalline form, we call it ruby or sapphire. So if it has a little bit of chromium as an impurity, it gets the color centers, which turn it into ruby. If it has iron or I forget what other iron and magnesium impurities, it can look like a sapphire. And so these are materials we're familiar with in nature. Now, Al2O3 can also, turns out, exist in many other crystalline forms. And it can also just be amorphous. Now, as soon as you say the word amorphous, it means you don't really know what you're talking about. Because obviously, if I say Al2O3, I'm talking about something with the short range order that says if I have two aluminum atoms close by, there are going to be three oxygen atoms associated with them. But if I say amorphous, I mean, there's no long range order. And of course, the transition from short range order to long range order can be done in an infinite number of ways. So there are going to be an infinite number of possibilities for what we mean by amorphous silica, amorphous alumina. And there are amorphous samples here that have been studied so in the laboratory. And so one of them looks kind of like this feature here, amorphous Al2O3 with a particular size distribution for the particles. But it has a strong emission feature out here that we don't seem to see. But some forms of Al2O3 measured in the laboratory. So this is what is thought to be gamma Al2O3, but really found in rocket exhaust from a rocket that used aluminum as the oxidation of aluminum as the propellant. And that shows a feature peaking at too short a wavelength, but no feature out here at 20 microns. So Al2O3, we don't really understand well enough to be sure exactly what it would look like, but it looks like a plausible candidate material. Nature does know how to make Al2O3. Obviously, on the Earth, we find rubies and sapphires, et cetera. But we also find in meteorites pre-solar grains. Here's an example of one pre-solar grain found in a carbonaceous chondrite meteorite, which is a 1 micron size grain. It's actually crystalline. So this is a corundum grain that we know is pre-solar because it has very unusual isotopic abundances. So some AGB star long ago made this grain. It left the star. It floated around the interstellar medium. It got trapped in the material that ended up forming our solar system, and ended up inside a meteorite that we had the good fortune to take apart on the Earth and study. Okay, so that is a plausible material. Now, why should the dust in 1 Zwicky 18 look so different from the dust in the Milky Way? We got stars in both galaxies. Both the stars in 1 Zwicky 18 presumably obey the same stellar physics as the stars in our galaxy. And so once heavy, massive stars have been able to synthesize heavy elements, you might have expected supernova ejected to look fairly similar to supernova ejected from core collapse supernovae in our galaxy. Maybe some dust is made in those stars. Massive stars that once a star has heavy elements in its outflow, a massive star is going to form dust, presumably similar in both galaxies, except, well, chemistry is going to depend upon the metallicity for sure. But you might have expected some similarities, but nevertheless, we don't see any evidence of silicates, and we don't see Al2O3 in our interstellar medium in amounts large enough to detect in the interstellar medium. We find it in a meteorite, but not no evidence of it in our interstellar medium. So my argument here would be that in 1 Zwicky 18, there are stellar processes making dust. The dust goes out into this very violent interstellar medium with supernova blast waves and H2 regions and all the other things going on when a star is energized in the interstellar medium, and it gets destroyed. And what we're left with is the toughest of the tough. So Al2O3 is a very refractory material, and you might imagine that it would survive longer than silicates in the hostile environment of supernova shockwaves. And so maybe that's why Al2O3 ends up being a favored species to find in 1 Zwicky 18. And maybe this is a guide to what we might look for in star-forming galaxies at redshift 10 or 15, once we have the ability to study them. Now, this ability to study the infrared emission from a galaxy at redshift 10 or 15, for looking at the infrared features by dust, there tend to be at wavelengths like rest wavelengths of like 14 microns or 13 microns. So we're going to need an instrument like PRIMA. So let's hope that science gets the PRIMA Space Telescope made available to study these things in years to come. So that'll be a great tool for studying what the dust is like in these very young galaxies when the universe is young. But we can look at a young galaxy today and find evidence that might be a very good guide. So let me just stop there and ask for any questions.
Great, thank you very much, Bruce. It's a great overview here, and I think I know you have results on the molecular hydrogen, which maybe we should come to as well. But why don't we take some questions now on the dust aspect? So raise your hands in Zoom, and maybe Ryan and Virginia can help me. So Al2O3 is not seen in the diffuse ice. Is it seen from any evolved stars in the galaxy?
There have been hints of it in evolved stars, very interestingly, in very low metallicity evolved stars. So if you look, there was Spitzer Space Telescope infrared spectroscopy of the mass loss from the collective mass loss from stars and globular clusters. And there were hints of a feature in the 14 micron region. Al2O3 is one of the things that was discussed as a possibility. Spinels are also discussed as a possibility. No definite interpretation of that. Again, the signal to noise are not fantastic. So that's the only hint that I know of of astronomical Al2O3 being shown up in our galaxy. Maybe somebody can inform me of other examples. And so we find it in meteorites. So we know for sure there has to be out there in the interstellar medium to eventually have been trapped in a meteorite formed 4.5 billion years ago when our solar system formed. But there isn't enough of it out there for us to detect in any way that I know of.
Hmm.
Maybe somebody knows of some observations, but please let me know.
Hmm. And then what was Gina's next, I think?
Yeah, hi, Bruce. Thanks. I'm curious actually about the spectral index of the dust. So I was reading a paper about a different compact dwarf, IC10, and there they found that the spectral index was zero point 0.5 or so, and something about dust destruction and things like that. So I'm wondering, for this galaxy, the spectral index seems to be reasonably constrained to 2 in the far infrared. Is that right?
Well, I don't think we know well enough. So if you go back to the Herschel observation, the Herschel and Spitzer observations, well, we have a clear detection at 100 microns. And I think there was a clear detection at 70, although again, when you're doing it with the big beams that the Spitzer beam was pretty big at 70 microns. And so, are you picking up some background galaxy that's trickling in that's sitting and contributing? We don't know. But at the longer wavelengths, we didn't have very clear detections. Even the 160 micron detection was not super strong, and then the beam is so big, there are other sources. It could be background contributions there. So I'd say we don't really know enough about the emission spectrum to be able to deduce the opacity law, given that, you also need to make assumptions about what the dust temperature is uh, to model the SED. So I would imagine you could probably model it just as well with a nu to the 1.5 opacity. So that nu to the minus nu squared, that nu squared opacity or lambda minus 2 opacity, well, that was just a provisional starting point here. But I don't think the results would have changed in terms of the quality of the fit. The temperatures would be a little bit different. If I'd used a nu squared, nu to the 1.5 opacity, then the temperatures would have been slightly lower, but the 50 might have changed to 45 and the 120 might have changed to 110. So I don't think it would have been, I don't think we could say. So the nu squared was just a proxy.
Can I follow up on the temperature? I'm just teaching this now and not in my class, but of course the small grain transient heating would have warmer temperatures. Do you think that would be a play here?
Well, I don't think we're seeing any evidence of single photon heating here. The temperatures we're seeing there are not unusual. We're looking at dust in a region where the starlight intensity is actually pretty high, right? We've got star formation going on here at the level of almost one solar mass per year, and
Mhm.
it's not in a very big galaxy, and there's very little dust there. So the dust is not blocking the light from the stars. So if you are a dust grain sitting in 1 Zwicky 18 in the vicinity of this star forming activity, you're going to be heated to a temperature of something like 50 degrees Kelvin rather than the maybe 18 degrees or 17 degrees that you would have at a typical point in the solar neighborhood where just the general starlight background is heating. So the 50-degree Kelvin, you don't need single photon heating to explain that in 1 Zwicky 18. The normal dust is going to be heated to temperatures like that.
Are these internally heated or externally heated clumps, do you think?
I don't think we know, except to the extent that since some of these regions do seem to have molecular hydrogen in them, it it would not be implausible to say that there are sort of surviving molecular clouds there where the stars that are now shining brightly are outside the material that is still molecular because otherwise it would have destroyed it. It's in the process of destroying it. But honestly, I don't think we know. We don't have the angular resolution to say much more than that we detect things in 1.3 arc second beams, but we can't talk about what the structure is on scales smaller than the 1.3 arc second extraction. I mean, we at the shorter wavelengths of Mira, yeah, yes, our beam size is smaller than 1.3 arc seconds, but the emission is pretty weak there. So
Mm.
those images I showed you were the mirror images, and we see fuzzy blobs there at on the 1.1 arc second
Mm.
scale, whether they're made up of a small number of compact things or one big fuzzy thing. can't say.
But we know where the hot stars are, don't we? So we know where the FUV sources are, presumably.
Yes, but again, we don't see the stars individually. HST, angular resolution is only a few tenths of an arc second, and so we're not picking up in the HST images. We're not picking up one star by star. We're not resolving them, but we're seeing star forming bright regions of active stellar emission. That was the HST image. You can see a lot of structure in it, but you're not seeing individual stars
Let's go
in
to
the blue.
Theme's question then.
Say again?
We're going to go to theme now.
Okay. Yeah. Thank you. Thank you very much, Bruce. A very nice talk. Yeah. So I just have one question about the destruction of Al2O3. So you mentioned here that Al2O3 is more resistant to destruction than silicate and hydrocarbons. So I can understand that from the point of view that the sublimation temperature of Al2O3 is much higher than silicate and hydrocarbons. But how about destruction by shattering, grain-grain collision? Is it still more difficult to destroy Al2O3?
Well, I don't know. I mean, it is a hard material, so silicates are, again, I'm not a mineralogist, so but somebody who knew silicates would be able to tell you what the hardness value of various silicate crystals is compared to the hardness of corundum. I think corundum would be harder, and maybe that's a guide to fracturing, but I would say we don't know. I mean, I'm sure you can fracture Al2O3 in grain-grain collisions, but remember, because the grain abundance here is so low, grain-grain collisions also become rare. So grain-grain collisions is a sort of a quadratic process for grains destroying grains, whereas the linear process of protons and helium and hot gas destroying grains, that goes linearly with the grain abundance. So I would imagine sputtering in a galaxy like this would probably be the major process, just because the general abundance of grains is so low. But still, shattering is certainly something not to be forgotten.
Yeah, thank you. So I just have one more question. So have you tried to add the contribution from iron? Because iron may be there, right?
Yeah. So again, this new squared opacity, I mentioned, well, that could be amorphous carbon. It could also be metallic iron. So I would say a candidate for the continuum emission here, metallic iron would be plausible. Some form of amorphous carbon would be plausible, and maybe other things as well. We don't claim to have a plausible identification for where the continuum might be, but and so there's a lot of uncertainty about the mass here, because if you're going to deduce the mass, if you thought it was actually metallic carbon, the dust mass would actually go up a little bit, because the metallic carbon opacity is a little bit lower than than the numerical value I was adopting, but in the ballpark.
So
thank you.
What fraction of mass would be in this alumina material compared to either this carbon compounds you're talking about or the?
Well, I think I estimated that again, for my provisional guess for what the opacity is of the continuum, and my estimate of the Al2O3 opacity based on laboratory measurements of these different materials, which none of them match perfectly, but they all give you values for the sort of integrated opacity in this 13 to 14 micron feature. I think I estimated something like 7% of the grain mass would be Al2O3. So I'm not saying the grains are all Al2O3. Just that Al2O3 seems to be a significant contributor to the grain mass. If that identification is correct. Again, maybe this identification is wrong and it's something else entirely. But there aren't too many other candidates that one can think of. Spinels, again, is one other thing that does have an infrared feature in about this wavelength range, and so you could talk about that composition. So that has aluminum in it as well. But not just aluminum and oxygen.
Well, I have more questions on the dust, but I think it'd be great if you could tell us a little bit about the molecular hydrogen part that you mentioned. So,
be happy to. Okay, so I'll try to move through this quickly because, okay, well, let's see. Where was I here? Okay, so back to this galaxy, the image that we have in the JWST filter photometry. So again, three bright sources down here showing up brightly at 11.3 microns. And then this northwest source, which I showed you before, as the fourth place, which seemed to have a hint of this 13 or 14 micron feature. And then a number of other spots here where we've extracted spectra where the emission, the signal to noise was high enough to begin discussing what the spectrum might look like. So I'll also mention that molecules have been looked for in this galaxy before, namely CO. So CO observations of this galaxy had a weak detection of CO 2 to 1 at one position, and that's this position right up here. So it was a weak detection. Interestingly, no reporting of CO emission down in this region here, a little bit showing up here. So not clear, how much CO is there. And so you could ask the question, well, we got a galaxy here that shows plenty of 21 centimeter emission, just the barest hint of carbon monoxide emission. Of course, you can have molecular hydrogen without having carbon monoxide, but are the stars forming out of molecular gas as they typically are in our galaxy, or are the stars forming out of atomic gas? We kind of think star formation will be preceded by formation of molecules, but we don't know that. Okay, so in this galaxy, in these spectra I showed you previously, there were strong emission lines. And this is an example of one of these two southeast positions, 1.3 arc second diameter aperture, where there are very clear detections. So the MIRI range I mentioned, MIRI goes nominally out to 28 microns and would have been sensitive to emission in the 28 micron molecular hydrogen line if it didn't have so much noise. But the noise in MIRI basically precludes detection of emission of the molecular hydrogen line at 28 microns. So we'll end up over this spectral range with 8 rotational transitions within the MIRI bandpass running from 5 microns for the J equal 10 to 8 to 17 microns for the J equal 3 to 1. And in this position here, we detect with signal to noise greater than 3, 6 of these emissions. So 3 to 1, 4 to 2, 5 to 3, 6 to 4, 7 to 5, 8 to 6, maybe, except this is not 3 sigma, and 9 to 7. So we've got a number of different lines here, and in some of the other apertures, also multiple lines. So in 4 apertures, we had 5 or more lines detected with greater than 3 sigma. So you can begin discussing what the distribution over the different rotational levels of these lines is, and then of course discuss what kind of mass of molecular hydrogen is needed in these excited states to explain the observations. So a very brief primer here because of time. I don't want to spend too much time on talking about this, but you have to remember there are 2 kinds of molecular hydrogen depending on how the nuclear spins are oriented. If the 2 proton spins are parallel in the molecule, we call that ortho H2, total nuclear spin of 1. If the 2 spins are anti-parallel, we call that para H2. And it turns out that for symmetry reasons, if the nuclear spins are anti-parallel, then the rotational quantum number of the molecule when it's rotating has to be even, J equals 0, 2, 4, 6. If the nuclear spins are parallel, ortho H2, then the rotational quantum number has to be odd. And because the process of flipping the nuclear spins is a very slow one, these two kinds of hydrogen almost behave like separate chemical species with very slow, relatively slow conversion of one to the other. So you can sensibly ask yourself, what is the ortho-para ratio that I need to reproduce the observations? Now, the ortho-para ratio, if the gas were in thermodynamic equilibrium, the very lowest energy state is the J equals 0 para state, and all of the molecular hydrogen would be in the lowest state if you took the temperature down to 0. So you would have pure para H2 and a 0 ortho-para ratio. At high temperatures, it tries to democratically sample the degeneracies of the 3 the nuclear spin degeneracy of 3 for the ortho and 1 for the para, you tend to have an ortho-para ratio of 3 at higher temperatures. And we think that newly formed molecular hydrogen starts off with an ortho-para ratio of 3 after formation on dust grains. And then in cold gas, you could gradually convert the ortho to para, and lower the initial value of 3 down to some lower value, maybe 1 or 2, or maybe say 2. And when we look around the interstellar medium, where we can measure the excited molecular hydrogen, we often find ortho-para ratios of something in the range of 2 in various regions. And if you had a shock-heated region, you could take the ortho-para ratio of, say, 2 and raise it back towards 3 if the shock-heated gas stayed hot long enough to accomplish this conversion. Okay, so let's look at the emission we see. We're going to try to reproduce the abundances of the molecular hydrogen in the different rotational levels that we detect with a model that, for simplicity, we know we need more than one temperature. You can't do this with one temperature gas. So the current way of doing this is to assume a power law temperature distribution. So we'll have a power law distribution where we have one free parameter as the power law index. Another free parameter will be the lower limit on the distribution. That turns out to be important for, could talk about more about that later if people want. And then obviously one parameter is the total amount of molecular hydrogen that you're distributing among these different levels. And then a fourth parameter would be the ortho-para ratio. If we allow ourselves to treat these two species separately, then we'll equilibrate the ortho among the different, according to the temperature we have. We'll equilibrate the para among the different levels according to the temperature we have, but we'll have the freedom to have whatever the ortho-para ratio is that gives the best fit. There's a fourth parameter here, which is the upper limit on the temperature distribution. That turns out not really to matter very much, because for different values that you choose, you get almost the same result. The value has to be a high value. Okay, so here's just one spectrum where we have the detection of the J equal 3, J equal 4, J equal 5, J equal 6, J equal 7. We don't detect J equal 8 significantly, and emission from J equal 9. If we try to fit that, we can do a pretty good job with an ortho-para ratio fixed to 3. So the blue curve here is a model, actually, Monte Carlo samplings over models where the ortho-para ratio is forced to be 3, and then we try to adjust the temperature distribution to get the best fit here. But it turns out that you get a better fit if you give yourself one more degree of freedom, therefore reducing the number you give them one more degree of freedom to adjust, and therefore reduce the number of free degrees of freedom. And then you can still get us to reduce the chi-squared per degree of freedom in the data by allowing yourself to vary the ortho-para ratio. And when you do that, the best fit value for this position is 3.55. Now with uncertainties. So this is position number 2 here. Here's position number 2. This shows you the uncertainties after doing various Monte Carlo samplings of the ortho-para ratio. They're all significantly above the value of 3 here. And the two different, the filled and the open symbol, just represents what you get if you set the upper temperature to 3,500 or the upper temperature to 2,000. It doesn't really matter. And then at 2 other positions here, we also get statistically different values values statistically different from the value of 3. Some positions we get less than 3, so we're not above 3 everywhere here, but we seem to have at 3 positions statistically significant detections of ortho-para ratio greater than 3. At a 4th position, we're greater than 3, but within the uncertainties, it would not be inconsistent with 3. So how do you do this? How can you get an ortho-para ratio greater than 3? So very simple interpretation here. So here's a scenario. Start off with gas where the ortho-para ratio is, say, 2. You've done the usual things in the interstellar medium. You've made dust grains on grain surfaces. It started off with a value of 3. The temperature is low enough that the value of 3 dropped to some smaller value like 2 or 2.5, and then form stars. star formation begins. You make massive stars. They're generating extreme ultraviolet radiation, which both ionizes hydrogen and dissociates the molecular hydrogen, drives an ionization dissociation front into the pre-existing the gas that was molecular before the stars were formed. Now, self-shielding comes into play. Ortho molecular hydrogen shields ortho. Paramolecular hydrogen shields para because the spectral lines, the ultraviolet lines, are actually different wavelengths. And so we have these two species, each able to self-shield, but the ortho self-shields better than para. So as this dissociation front is advancing into the molecular gas, it's destroying the para. The para molecules have shorter lifetimes than the ortho molecules. And so you're gradually raising the ortho-para ratio by selectively destroying para more rapidly than ortho. So in principle, you could raise the ortho-para ratio to very high values just before the last molecules are gone. Now, we don't see this in the Milky Way. When we look at the ortho-para ratio in, say, the Orion PDR, we don't find values greater than 3. I think the reason for that is that our PDRs have enough dust in them that they basically are quasi-stationary. The ionization dissociation front starts going into the gas, and then it propagates relatively slowly so that at each point in the ionization, in the dissociation region, you have almost a balance between H2 formation and destruction. Not exactly a perfect balance. There is perhaps advection going on here, but to first approximation, it's a stationary PDR, and that's in fact what people usually model is a stationary PDR. So when that's happening, you're remaking the molecular hydrogen with an ortho-para ratio of 3, and you end up with values that in the gas that end up being measured to be close to 3 or a little bit below. But in 1s-Wiki 18, we just have so little dust there that when this dissociation front starts marching into the molecular cloud, the reformation process is just not important. We're just destroying the molecular hydrogen. The reformation is a minor perturbation on the story. And so we end up having this ability to preferentially destroy the para, leaving ourselves with an ortho-para ratio of greater than 3. And I'll remind you, these regions we see here, not remind you, but the column densities of molecular hydrogen that we see in these regions don't correspond to very large molecular hydrogen masses. But we also have to remember we're only detecting levels J = 3 and above. There could be colder molecular hydrogen in regions where the dissociation is not already going on rapidly enough to heat the gas. So we're not claiming to detect all the molecular hydrogen in this galaxy, but we're detecting enough of it to have an interesting story to tell. So I'll stop there. Thank you.
Great. Well, thank you again. Another round of applause. I think it's deserved for that. Any quick questions on the molecular hydrogen? So that's something I haven't heard about much before. So here, John, please, you're the expert from our side here.
Oh, John, great to hear from you.
Yeah, it's great to see you too, Bruce. Yeah, of course, I have to propose an alternative explanation for the molecular hydrogen. That an excitation diagram taken directly from the emission line intensities also has the characteristic of what you would expect from strong ultraviolet fluorescent excitation. And again, as you said, you observe directly only the molecular hydrogen in J = 3 and higher. You don't know directly from the observations how much, even in a uniform region, how much is in J = 0, 1, and 2, which accounts for most of the total abundance of the H2. And when you talk about accomplishing a greater than 3 ortho-para ratio by having photodissociation that exceeds the formation rate, is too fast for the formation to keep up. That also implies that the fluorescent excitation rate, which must be 5 to 10 times higher than the dissociation rate, must be large and affecting the excitation of the, or has affected the excitation of the molecules in the past. So I would wonder if perhaps the assumption that there must be a varying kinetic temperature is limiting the possible explanations of the observed excitation.
Well, first of all, I completely agree with you that the UV pumping story is one that could well and I think ought to be very important. So I share your bias here that the UV pumping is going to be important. Unfortunately, the MIRI spectroscopy doesn't give us much of a handle on that. There are a few lines there which, would show up, if we had extremely high signal to noise, but the lines we're seeing that we have the ability to see don't tell us anything about the UV pumping story. Leslie proposed for near spec observations, but the JWST TAC, for some reason, didn't think that was worth doing this time. But it's just the obvious thing to do. I mean, it blew my mind that the proposal to use near spec after these molecular hydrogen was detected in this galaxy with MIRI, that wasn't approved. But at some point, somebody will do that. It just has to be done. But it doesn't seem to give you, so it may be responsible for the excitation we see, but I don't think it explains the ortho-para ratio greater than 3, because if you have optically thin pumping, then you would just see pumping in proportion to the population that you have. And so the ortho-para ratio is less than 3, and optically thin pumping would give you value less than 3 for the pumps. If you have optically thick pumping, then the ortho is actually suppressed. So you would lower the apparent ortho-para ratio in the fluorescently pumped emission. So I don't think that can explain. I think it's responsible for part of what's going on, but just the pumping process, I don't think gives us the low ortho-para ratio.
Well, again, because the molecules in J equals 0, 1, and 2 are, in a sense, hidden from observation. That if you have a stratified PDR that's accounting for this emission, that some of this apparent high ortho-para ratio is just an effect of the integral through the atmosphere, the radiating atmosphere, perhaps.
So
maybe we can follow up. Yeah,
maybe
go ahead.
Fast.
Go ahead, Brad.
I also have to run to a meeting really like a couple minutes ago, but I just want to comment that so we have new 3D models zooming into the actual photo dissociation front where we resolve all of the fronts, and we have the full H2 level population now in there. If you run an Orion bar-like model, you do get ortho-para ratios greater than 3 before the H2 dissociation front, but when you then start trying to say what is the ortho-para ratio where you get the bulk of the emission, it sits at around 3, which is also what the PDRs for all teams do. When I ran a very low metallicity run, the dissociation front came, of course, much more into the cloud, so we can actually resolve this and we see all the structures. And again, you get very high ortho-para ratios. So we are actually getting ortho-para ratios of like 10 or higher in the very diffuse gas. But again, when you look at where do you see the emission, the ortho-para ratio is about 3 to 4. So this is, I mean, if you kind of weight the ortho-para ratio based off of where you would see the emission, for the lower metallicity, it gets up to about 3.5, 4. And for the Orion bar, it's basically at 3. But now because we have the models in 3D, maybe we could actually start to look at what is the mechanism that's causing this, because we can then look at exactly what the UV field is and the temperatures and everything in pretty high detail.
But you don't think it's just the preferential photodestruction of the para?
It's probably, but in our models, I mean, in 3D PDR, we don't fully resolve the spectra. I do have a subgrid model basically built into there to do preferential photo dissociation if it happens. So there is kind of an analytic subgrid model to basically weight the photo dissociation rates for ortho-para species. But it's probably a bit of a combination of both the UV fluorescence and the preferential photoassociation. There's also the fact that because the gas temperatures don't get very hot, so we get gas temperatures in our models of a few hundred Kelvin, but not quite up to as hot as you get in the Orion bar because you don't have the photoelectric heating as efficient. It kind of sits in that sweet spot too of getting a lot of the ortho to para rates for warm gas interactions. So maybe there's kind of a mix of multiple things that are all kind of preferentially bumping it up a little bit.
Well, it sounds like there's scope for improving the simulation aside, but what one puzzle would be then why it's not seen in the Milky Way, right? Or in various environments, it's higher than 3 has only been seen here. Is that right, Bruce?
Well, to my knowledge, maybe Brant has an update on that. I thought every time we look in the Milky Way, we find values that are sometimes up towards 3, but never in excess.
Yeah, not really.
I think, Bruce,
my models don't go
excuse
higher
me,
than
there were some Spitzer observations of H2 in shocks, actually, that David Neufeld and one of his students or postdocs did some years ago that showed anomalous orthopara ratios. And they had an explanation to do with the structure of shocks to explain that.
Okay.
I'll look up the reference and send it to you.
Yeah, I would appreciate that. I was not aware of values greater than 3. So,
well, there's more to discuss, but we should wrap up the main session now, and let me end the recording now. But let's thank Bruce again for a great talk and discussion.